All right, here's something from our textbook. I'm going to honestly kind of gloss over this, but I just want to point this out because this is handy for some applications. In other words, where is the normal force? And I've said before that the normal force is kind of right underneath it for a box. If it's rotating, then I put the normal force at the point of rotation. However, there is a place where we can draw the normal force that is helpful when we evaluate the tipping condition. Doesn't really do much for us in the slipping condition, but if we want to evaluate the tipping condition, what we can do is we can define a pseudo point through which the normal force acts. For example, we can just say that, I'm going to just draw it up here at some point on the body at some distance x from maybe that point there. If we say that this is the center line of the part, we got some some gravity here coming down. If I sum the moments about the point, sum the moments about the center of gravity, then I do have to take into account that friction force, and then I have to take into account this lever arm for the normal force. If you say that it is impending slip, we know that the force of friction is equal to mu normal, and then the normal force times this lever arm can help us solve for the tipping condition. So here's the deal. If the normal force lies on the body, then it is a non-tipping occurs. If the normal force, if x, normal force is on the body, then no tipping occurs. If x is off the body, for example, when you solve for this x, it's way out here, then that means that it's a tipping situation. And there's a good example here in the textbook, and you should walk your way through that if you're interested. And I suggest that this method can help evaluate tipping in its current condition. However, it does not generally help us solve for the force of friction to tip or the angle to cause tipping. So I actually find limited use for this method if in practice. So I won't be using this in terms of our lecture or our processes, but it is there for your use if you want to use it. Well, here's another tipping or slipping problem. What I've got here is a gentleman pushing on this barrel. He's pushing at an angle, and we're going to try to find out some things. It says the drum has a weight of 100 pounds. It has a static coefficient of friction of 0.6. It's got some dimensions. We want to find out the smallest force that will cause impending motion. So again, impending motion, we have to kind of understand what does that mean. Well, there are two possible impending motions. It could slip or it could tip. So those are the two conditions we're going to evaluate. Next thing to look for is the center of gravity. If the center of gravity is not drawn on the picture, then look for some indication of where it might be. In this case, it looks like the drum is a uniformly distributed, the weight might be uniformly distributed, so I'm just going to expect that the mg is in the middle, or the center of gravity is in the middle. So let's go ahead and draw a free body diagram with that assumption. All right, so center of gravity, there's going to be an mg going down. It's got this pushing force here coming off at an angle. So I'm going to draw the two components because those are kind of handy to have. And this one is a 3, 4, 5 triangle. So this will be 4/5 of P going in that direction, and it'll be 3/5 of P pushing down there. I have a normal force, and there will be a force of friction. Force of friction is going to resist the impending motion. It should be moving to the right, so force of friction goes to the left. All right, let's see what we got. Let's evaluate the slip condition first. Now I'm going to start with some of the forces in the y, and the reason is because I need to know that normal force before I can evaluate what happens in the x direction. So some of the forces in the y is equal to 0. So here I've got minus mg, but I also have a component of the pushing force. So that's minus 3/5 of p plus normal is equal to 0. The weight here of the barrel is 100 pounds, so normal here is equal to 100 plus 3/5 of P. All right, how do I get the slip condition? Or the next equation I'll use sum of the forces in the x is equal to 0. So in this case, I'm pushing with 4/5 of P minus the friction force, and the friction force is equal to mu normal. It is mu normal because it's a slip condition. That's equal to 0. So 4/5 of P minus mu, which is 0.6. The normal force is 100 plus 3/5 P equals 0. And you can solve that for P. P is equal to 136 pounds in order to make it slip. All right, how about the tip condition? What do we do for that? Remember, at tip, the normal force goes or moves to the point of rotation. So I'm just going to move that over there. Normal force now moves over there. I'll call that point A and this B. And then B goes to 0 at the tip condition. So let's go ahead and just write that down. At tip, rotates at A, and B goes to 0. And then when we find a point of rotation, which is right there, we notice again that A goes through that point of rotation, force of friction goes through the point of rotation, B has already gone to 0. So all we do is sum the moments about A, and let's see what we get. So here I've got the 4/5. Oh, now here we have to be a little bit careful. We have 3 forces to consider. That one times this lever arm, this one times this lever arm, and this one times a smaller lever arm. So I have to keep them all in there. So let's see what I got. Minus, come on, got that marker instead of a pen, minus 4/5 of P, and the lever arm here is 3. So that's the height. This is, I already forgot to put that. 3 is equal to that, and 2 feet is there. So again, always moment equations always have to have lever arms, so that'll be 4/5 times that, and that is going in the negative direction. All right, I have plus 3/5 of P, and it has this lever arm, which is this total length, which is 2. I also have mg, and it has a lever arm of 1. In other words, it's going to be half the total distance. This is 2, and this is going to be half. All right, so that's equal to 0. I have a weight of 100 pounds, and I can solve this for P is equal to 83.3 pounds. All right, which one wins? Well, it's pretty obvious that the pushing force to tip it is the smallest one, so we declare this is the condition that will occur first. Now here's just another little concept, is that what happens to the man? In other words, the guy here is pushing on this. Let me scooch this down just a little bit. The guy is pushing on the barrel, and he needs 83 pounds in order to make it move at all. We discovered that it will tip before it slips. The question here is, how much friction does he have to have in order to make that happen? So I just want to suggest here that there are 2 types of friction, and I don't really mean that in terms of fundamentally 2 types, but there is friction that makes you slow down or keeps you from moving. And there's also friction that makes you move or helps you move. So I call it friction that makes you slow or friction that makes you go. So in this case, what I have for the man is I have some friction that's going in this direction to help him move in that direction. So all we have to do is draw a free body diagram of the man. So what we're looking for here is the coefficient of friction between the man's shoes and the floor. So let's draw a free body diagram of the man. He weighs 150 pounds. The force that he's pushing on the barrel is pushing back on him equal opposite. So if I have 3/5 P going up and 4/5 P going that way, I should be able to find out what the force in the Y is. So I have minus 150. And then coming up, I have, see, the mg is going down, so I have coming up is the normal force plus 3/5 P. So I can find that the normal force is equal to 100 pounds. In the x direction, some of the forces in the x, or what I want is the minimum coefficient of friction required, which means that I'm evaluating this as a slipping condition. So I'm saying the force of friction max is mu normal. The normal force is only equal to 100 pounds here. Sum of the forces in the x is equal to mu normal minus this 4/5 of p. And again, p is equal to 83.3. Solving this for mu, you can see that it takes quite a bit of friction in order for him to accomplish this, 0.666. We'll discover more about coefficient of friction and what's a reasonable coefficient of friction as we move forward. So what is the force of friction really? We've talked about it being a reaction force, and it can never exceed the maximum force of friction, which is mu normal. But if it's not slipping, then it will be less than mu normal. So let's just look at this one really quickly. I'm pushing on this box with a 100 Newton force. It weighs 50 kilograms, and it's got a coefficient of friction of 0.25. If I say that the force of friction max is equal to mu normal, which is 0.25, the normal force here is 50 kilograms times 9.81. That's equal to 122.6 newtons. So again, if I draw a little free body diagram here, force of friction, if I said that sum of the forces in the x is equal to 0, if it is not moving, then 100 newtons minus the force of friction has to be equal to 0. So how do I know if it's moving or not? Well, I need to have at least 126 newtons to make it move. I'm only pushing with 100. Therefore, the force of friction in this case is just a reaction force. It is force of friction is this. That means this box is in equilibrium as it sits, and then the force of friction is just equal to 100 pounds or 100 newtons. Sorry, 100 newtons. So this is kind of a concept you'll have to be able to evaluate in a variety of ways. Is it moving or not? What would be the force of friction depending on whether it's moving or not? And I will give you some homework problems for you to play with on that. So here we have a car that's being pulled up at an angle here. And what we're looking for is what is the towing force to make this thing move. This is a little bit more complicated just because it has 2 points of contact that have different coefficients of friction. And we talked about if the coefficients of friction of the contact points are the same, then all we really have to worry about is just one normal force. However, if the coefficients of friction are different, then we have to worry about, or then we have to analyze the normal forces at every contact point. So in this case, it says the back brakes are locked, the front wheels are free to roll, so clearly that indicates differing coefficients of friction. So what we have to do is apply the friction force at where it occurs. So in this case, I'm going to draw a free body diagram with an mg, a normal force at A, and then the friction force applied at B only, not at A. The force of friction here, the pulling force comes at an angle, so there's a cosine component this way and a sine component this way. Each of those, regardless of how we do our moment equation, each of those will have a lever arm, because if you look carefully at the picture, this has got a 0.3 meters off the floor, and this one's got different lever arms depending on whatever you're summing your forces about. So let's moments about, beg your pardon. So anyway, let's sum the forces in the x and see what we get. So here I have minus F cosine plus the force of friction at B is equal to 0. Because we're at the slip condition, the force of friction at B is equal to mu B. I'm given mu is equal to 0.3, but I don't know the value of B. So I'm going to just set this equation equal to B, and it will be a function of the force and the coefficient of friction. Now, to evaluate the normal force at B, it's often easiest to sum the moments about A. And you'll get used to that if you haven't already. So I'm going to sum the moments about A. So here I've got the cosine component times his lever arm right up there. I've got the sine component going in the other direction. And his lever arm is right there, which is 0.75. Got mg. It's also going in the negative direction, and there's the lever arm for that. Then I got B up here, and it's got a positive force, or positive moment direction, and it's got that whole lever arm, which is the length of the wheelbase there. That's equal to 0. So now I have two equations, two unknowns, got a B and an F, and then F and a B here. I can set this equal to B or plug this B into here, and then solve for the pulling force, which is 2762.